All right. So let me again start by asking you if you have any questions first before we proceed further. All right. So we talked about this idea of using the flux concentration, and we talked about what becomes travel times. So let me talk to you about depth moments. So we just talked about what we call as time moment, temporal moments, because we are observing flux concentrations as a function of time. What we also said was if I do have the flux concentration and under right boundary conditions meaning at the inlet end all the solute is introduced instantaneously, then what we get as the flux concentration C sub F, for different distances, if I could compute this or estimate this, and what with the total mass applied divided by Q, essentially this became the travel time distribution. Okay. So since this is a function of x and t in general, for instance, if I'm using the ADE model, I can compute C sub f of x of t as we have done. So let me say I call this as f sub f of x of t to indicate that this is based on flux concentrations. It's a probability distribution function. It talks about travel times. So that let's say this is time, and let's say this is what we get as f sub f of x comma t. So this is time. So at a given location x, okay, I'm going to get this kind of a curve. Okay. So let's do that at x equals some quantity x prime. Okay. What I want to now do is introduce the idea of depth moments, and this will begin to answer some of those questions. As you have told us we have data in terms of time, is that the only analysis that we can do. So let me introduce the idea of depth moments. So what we are going to do is, now look at it a little bit differently. So is my mic going on and off? Okay. So now I have essentially this as my length of the column as my axis. Okay. And at a given time, t equals 0, such as the previous experiment, with a semi-infinite column. At location 0, at time t equals 0, I introduce a certain mass of solute. And after a certain time, I basically see how much concentration is there along the column. And ideally, I would like to know what the bulk concentration is. So this is what we do in many experiments, is in many laboratory column experiments, we take a long column, introduce a solute, and after a certain time we stop the experiment, bring the solute column and chop it off into pieces, and within each piece take the soil to the lab and extract all the solute that I can, which is in solid phase, liquid phase, gas phase, I don't care. So we use extraction methods and remove all the solute. So what we get is bulk concentration, and then we can get that as a function of location. Okay. What I want to do now is interpret that in a different way. Whatever bulk concentration or residence concentration, I want to think of that as another probability density function. Okay. So the way I choose to interpret it is, all these particles were released here at time t equals 0. At a certain time, at some time, when I look at where the concentration is, this gives me an idea of how far the solute particles have traveled at that time. So now my random variable is travel distance. Okay. At a given time, how far my particles have traveled. And because I observe different amounts of solute mass at different locations, just as our previous experiment, I interpret that as travel distances. So now my random variable is travel distance. Okay. And if I could construct such a distribution, let's say I'll call that as f sub r of x comma t. Okay. So f sub f of x comma t was my travel time distribution at location x. Okay. Now this is x. Because it's based on resident concentrations, I'm going to use a symbol subscript r to denote this travel time, this travel distance distribution. And based on how much solute mass I basically see in each of these soil sections at different distances, I'll now get a different shape of the curve, whatever it looks like. Okay. So this curve essentially is a function of x, but it's observed, let's say, at some time t equals t prime. So I stop the experiment at t equals t prime. This is what. So, when we do column experiments, typically we have many columns, many columns. We start all of them with the same initial conditions, same things. And then at different times, we will take one column and sacrifice it. We basically break it into small sections, do this kind of analysis. At some other time t prime, t double prime, we take another column and then do the same thing. So we'll get a different resident concentration as a function of time, or bulk concentration as a function of time. Okay, and then if you have many columns, you therefore get many of these. But they are fairly time-taking. It's a painstaking experiments. But I want to ask ourselves a different kind of question. Okay, so this was at equals t prime. Okay, so let us say this is t prime. Then since this is a probability density function of travel times, so at a location x equals x prime, at that location, so let us say this is x-axis. I think of this as x equals x prime. So I want to now sort of relate these two quantities. Okay. Ideally, what I would like to do, if I have a column and I do an experiment and I get the flux concentrations, I get my residence time distribution function, I want to ask myself, now do I have to do a whole different set of experiments to get this? Or is there an easier way for me to get to that? Because that would be far more desirable. Doing all those column experiments will take a lot of time and a lot of effort. Okay. So I look at this. So this shaded area tells me that at a location x equals x prime in the column, if particles were released at time t equals 0, this is the fraction of particles whose travel time, at x equals x prime is before this. Okay. So it's less than t prime. What does that mean then? All these particles, at time, all these particles, or this fraction of particles at time t equals t prime, would have crossed the distance x prime. Okay, because their travel times are less. So I come over here. If this is x prime, I take this shaded area. Okay. So now these are travel distances. So the same particle, the same set of particles, if they were released at x equals 0, this tells us with their travel distances. Okay. If all these particles had a travel time less than t prime, that means all of them have crossed x prime. They're traveling faster. Okay. So what that means is, for the same experiment, if this interpretation has to work, if this is travel distances and this is travel time, these two shaded areas must be equal. Right? Because this says that this is the fraction of particles for whom the travel time was less than t prime. So basically they were traveling faster. by the time we come to x prime, they would have essentially crossed. So if I do this, find the travel distances, this is my distance x prime, those fraction of particles have already crossed x prime. Okay, so those two must be equal. And then, so that statement, if you will, is reflected over here. It says 0 to t, this area, under the flux concentration or the travel time PDF, should be equal to x to infinity in the residential or in the residence PDF, travel distance PDF. These two are equal. And if those two are equal, I can differentiate both sides with respect to space and time. I'll get this equation. Okay. So what this says is the derivative of the flux concentration or the flux PDF with respect to x plus the derivative of the resident PDF with respect to time. So the flux PDF is for travel times. The resident PDF is for travel distances. So this must hold true. Okay. So what this then allows me to do, if I have this relationship, that is allowing me to relate, let's say, flux PDF to a resident PDF. And that basically means, I have a way to work with this. But I also maintain that this is, we talked about the continuity equation. When we're talking about solute transport, our continuity equation, if you remember, looks like this. When we did the control volume analysis, we said this is the bulk concentration of the control volume. This tells us about fluxes coming in and leaving. So this is our continuity equation in terms of solute mass. That equation over there, which looks like I claim are equivalent. In some sense, this is conservation of probability mass from travel times to travel distances. Okay. So how do we essentially also look at this? Notice that Q sub S, okay, Q sub S, we had essentially defined that as the concentration, the flux concentration times Q. Okay. So Q sub S was that. C sub F was the flux concentration. The flux concentration probability density function, we had said that F of F must be C sub F divided by M over Q, right? So I have Q sub S over here is C sub F times Q, but C sub F itself is F sub F times M over Q. So from this equation, okay, what I have is this last term over here is Q sub S, which is Q times M over Q and this is of course del CB del T. So these two equations must be same. So if this is del F del X for the flux concentration I have over this, F sub R then must be equal to C sub B divided by Q this is equal to F sub R. Right? Notice that when we have been doing all of this all the time, we have been setting this quantity M over Q equal to 1. Even when we're doing advection dispersion equations, we're setting that equal to 1 for the math to work out. But what we're essentially saying is, if we measure flux concentration, I have to normalize with this quantity to make it a flux PDF, for it to become a PDF. Okay. So if this quantity is 1, that means under the same boundary condition that we talked about, okay, if I am measuring the bulk concentration all along the column, if I divide that by small q, the Darcian flux, that is my resident concentration distribution, resident travel time distribution. Okay. So this equivalence, so both of them are actually continuity equations of sorts. This was our model for mass continuity. This is my probability continuity equation. Allows me to relate travel times and travel distances. So that is also very useful for us. One of the things that you would notice or you will recall that when we are doing these advection dispersion models, we had expressions for CF hat. We were only taking Laplace transforms. We were doing CF hat and saying, okay, with CF hat, I can use its moment generating quality and find moments. But once we found CF hat, we were also able to obtain C sub B hat also. So if you look at your notes, with each of those models weights, we had C sub B hat as well. So with C sub B hat, and dividing it by small q, because all those models had m over q already set to 1, I'm actually now able to get f sub r hat, because I have C sub B hat, small q is a constant. So whatever we did so far, it essentially naturally allows us to go to travel distance distributions and therefore compute travel distances, moments, and now we can talk about Eulerian moments or Eulerian properties. Okay. So this is our sort of motivation for how we do this. So this is the second, I guess, if you think of Harris's method, this is more bothersome, it's going on and off. So if you think of Harris's method as one of our first key results, because it simplified the analysis tremendously, this is the second key result. Because with one measurement at the outflow end, I'm actually now able to say something about what is happening within the column, what the travel distances are, and essentially do that kind of analysis. And we will see how we can do it both for advection dispersion type of models and even for stochastic convective type of models. So very, very useful tools, right? So this is what we have over here. So obviously from here, if I have the information for f sub f, I can construct f sub r of x of t simply by integrating with respect to x, so that I'll get this expression. Again, the column is initially solute free. And what it also means is, because we computed the transforms, so the Laplace transforms of the flux concentrations already, the Laplace transforms of the spatial travel time distributions is simply this quantity. So what we have done is we have taken this, by definition I'm multiplying both sides by e to the power of minus st, integrating both sides from 0 to infinity. Then this quantity by definition is the Laplace transform of fr of xt. Over here I have one integral going from 0 to infinity e to the power of minus st, all of this. I do integration by parts and I essentially end up with this. Also very useful. Why? Because everything that we did with the ADE allowed us to calculate this part. I can now calculate this part. Okay. Notice that we never actually try to calculate the entire distribution. We just take the transform and see if I can get to moments from there. Okay. We are going to now define something else. We talked about temporal moments, and temporal moments, which we had defined earlier in the morning. Okay. So remember, those look like mu sub n equals 0 to infinity. It was definitions in terms of time. And in this context, that would have been f sub f. So f sub f is same as c sub f, as long as m over q is set to unity, and we have an instantaneous release. So this was time moments, 0 to infinity. We are going to define depth moments, also 0 to infinity. So our column is still semi-infinite. My boundary condition is at x equals 0, and that will become important. So this is my next definition of another kind of moment. We'll call it as depth moments, and I will, at least for now, deliberately distinguish it from spatial moments. Spatial moments will require it to go from minus to plus infinity, which means I have to have an infinite domain. So we'll look at that a little later. So depth moment, let me define it like this. All right. Now notice that this integration over here is in terms of x. Okay. So if this is my depth moment, if I take Laplace transforms of both sides, it will tell me that xn hat, which is the Laplace transform for xn of t, is simply this equation. Instead of f sub r, I'll have f sub r hat. Okay. The other stuff is in terms of x. Laplace transform integration is in time. Also very useful because so far we have developed all kinds of expressions for f sub r hat. Okay. So this sets the context for us for depth moments. And I guess the useful thing is both of these equations are essentially continuity equations. So let us go to the advection dispersion equation. Okay. So advection dispersion equation, this is the resident concentration. Notice that x sub n hat is now the Laplace transform of the spatial depth moment. It will simply look like this. The reason why I do this is f sub r hat of x of s, we already showed it to be this quantity for the ADE, okay, where c was equal to this. Now, I think I've skipped several steps over here, unfortunately, but I'll try and explain this then. So this is x sub n hat. So if I have f sub r hat like this, what I can do is I can substitute this over here, okay, 0 to infinity. If I then what I'm going to get is x to the power of n. This stuff is essentially a constant. This doesn't contain x anywhere in what I'm doing. I have v sub x over here. This is the only place which has x. The rest of it, v over 2d, 1 minus c, c is positive, greater than 1, 1 plus 4sd or whatever, right? So 1 minus c is negative. That means this is exponential times a negative number. Let's say we call that as minus 8 times x. It so happens, just, sometimes things work out in our favor like this. It so happens that 0 to infinity of x to the power of n times e to the power of minus ax has a very simple solution. Okay, it's a closed definite integral. I don't remember what it is. I would have to look it up. But I can do that, and I get an expression for x sub n hat, which looks like this. All right. So Laplace transforms of depth moments, I'm going to get a very simple expression. Any questions so far? So now what we essentially are stuck with is, if I have these expressions for x sub n hat, I need to substitute x sub n equals 0, x sub n equals 1, x equals 2, and take their inverse Laplaces. And I would get x sub n back. So we go ahead and do that. So if I do x sub 0 hat, that means for n equals 0, x sub 0 hat is simply 1 over s. Its inverse transform is 1. So the 0th spatial moment is 1. Should be no surprise. It's a probability density function. Its area underneath it should be equal to 1. X sub 1 hat is this quantity. X sub 2 hat is this quantity. Okay? And it's a little painful to actually do the inverse Laplace transform, but you get these long expressions for x sub 1 and x sub 2. So that is your expression for the first spatial moment and the second spatial moment, all in terms of t. So what that says is, this curve that you are seeing is given by that expression. If I change t equals, if I put one value of t, I'll get one curve. If I put another value of t, I'll get another curve. x1, if you recall, because it's the first spatial moment, the first spatial moment is essentially saying what is the mean travel distance of the particles. The second moment is telling something about how much spread is occurring, if I can calculate the variance about the mean. How far is the centroid of the plume moving in time? Okay. But these are long expressions. For large values of t, whatever we think is large, these will simplify to something that looks like this, which essentially means that for after sufficient time, the rate at which the plume will move forward, according to the first moment, is going to be proportional to time. The proportionality constant is velocity. No surprise over there, because that's how we think the plume should move. But that velocity that you have is not realized immediately. You have to wait for some time. Similarly, the variance, or the second moment, x sub 2, is going to look like this after sufficient time. And then if you were to do the variance, that would look like something like 2 dt, but after a long time. Okay. So this was one of the questions that had been asked, I think, of Professor Srivastava when he was saying, what are these shapes going to look like with time? These are not Gaussian. They tend to be Gaussian for long times. The reason is a boundary condition. So in this case, what we have done is, recall that we have put an amount of solute mass over here. It's only allowed to move in the forward direction. There is no soil column in negative x direction. Okay. So basically, initially at small times, the spread of the plume will be very skewed. After a time, it will become gradually more and more and more towards normal. But initially, because of this boundary condition, you actually have a very skewed distribution. Okay, this is for depth moments. All right. So this is one important realization for us then. So for large values of t, in this particular construct, we have this issue. But we are able to get, so x1 gives me some idea of, how is the centroid of the plume changing with time. How it moves with time, we have this. x2 is the second moment, which says something about how it's spreading with time. And we have another expression for that. But these are fairly long. Part of the complication being because of our semi-infinite column and for the domain that we have chosen. Any questions? All right. Okay. Now let's look at infinite domains. Infinite domain is a different problem. So I'd have now a soil column that's very long, goes from minus to plus infinity at time t equals 0, at wherever I initially introduce solute, I'll choose that as my origin, and I'll essentially leave a certain amount of solute mass over there, and then allow it to spread and move along. Okay. So after a certain time, the plume is going to spread, and now several interesting things are going to happen. Because of dispersion, some part of the plume is going to go in the negative x direction, okay, whereas some part of it is going in the positive x direction. So a couple of things. So if I basically have trying to recover all concentrations, so at some x location over here, if I have a port and I'm measuring concentrations, the concentration will start from 0, rise, and then die down. Okay, but eventually, the whole plume. If I have a port over here and I'm measuring resident concentrations, because the plume first tends to move back and then eventually gets carried forward, concentrations are also going to go up and down. So you have to worry about what that means. Okay. So now let's look at this problem. My governing differential equation is now in terms of resident concentrations. Same governing. What has changed? The boundary condition is different now. My resident concentration at time t equals 0 is a delta function in x, which means at x equals 0, all the mass was added. Mass of solute is m. I divided by the total porosity, assuming it's completely saturated, for this to work out as a concentration. And then at plus and minus infinity, everything is 0. Concentration, its derivatives, and so on. So that's my problem. And then again, I'll set m over eta. I'll call that as 1 because I don't want to carry that everywhere. That will become my normalization constant to make this look like a PDF, just as we had m over q when we were measuring flux concentrations. And now I'll define spatial moments. Okay. My definition for spatial moments, again, I've used xn, but I've added a prime to indicate that my integration is going from minus to plus infinity instead of 0 to infinity. 0 to infinity, we had called that as depth moments. They're also spatial moments. We are doing spatial moments, but I want to distinguish them from the conventional spatial moments, which go from minus to plus infinity. This is my definition. What do I want to do? I want to solve for these moments. Okay. So essentially, if this is my expression for x sub n of t, minus to plus infinity x sub n, there are several ways we can do this. One of that is Fourier transforms. Because remember, Fourier transform was going from minus to plus infinity. If I multiplied by e to the power of minus I omega x, let's say the forward transform had the minus sign, e to the power of minus I omega x, that was also a moment generating function. It was generating spatial moments. So just like we did Laplace transforms for temporal moments, I could do Fourier transforms on this. And maybe we will see that a little later. But I also want to introduce you to another way of doing this. And what that requires is that I take each of those terms, multiply that with x to the power of n, and integrate from minus to plus infinity. Okay. So basically, when I do that, the first term over here is c sub r del t. If I multiply it with x to the power of n, this integration is in x. This is a derivative in time. The derivative simply comes inside the integral, and you simply have dxn prime dt. Nothing changes. The spatial derivatives are with respect to x, so you have to worry about that a little bit. Okay. So if I'm trying to do, let's say, minus to plus infinity, I have x to the power of n dx, right? So again, I can do this with integration by parts. So this will be x to the power of n c sub, wow. C sub r, I have minus, I have minus n 0 to infinity x to the power of n minus 1 c sub r dx. Okay. This is supposed to be minus infinity to plus infinity. That's integration by parts. At minus and plus infinity, c sub r is going to 0, so this term will drop out. And this will become, by definition, xn minus 1 hat, because it's a one order lower moment. I can do the same thing for the second derivative. For the second derivative, therefore, I'll have 0 to infinity, minus to plus infinity, x to the power of n x squared dx. And you can carry it through. What I'm going to get is n times n minus 1 x prime of n minus 2. So it's another integration by parts. Okay. So what that means is, when I have terms with these spatial derivatives, I use this definition. I can basically, what I get is the spatial moment of a lower order, depending on what derivative I'm taking. So I can make these substitutions. I can go ahead, multiply all terms by x to the power of n, integrate from minus to plus infinity, I get this equation. Okay. And given these boundary conditions, the 0th moment of x0 prime at t equals 0 is going to be 1. All the higher order moments are 0 because I introduced a delta function. All the solute mass was at x equals 0 at time t equals 0. So the 0th moment is 1. After that, all moments, higher order moments, are 0. Okay. So what do we have then? Okay. So now I've taken the partial differential equation and converted into differential equation, which is in terms of moments. My unknown quantity now is a spatial moment. So that is a moment governing differential equation. Okay. We will talk more about moment governing differential equations later, but what we have are differential equations which essentially tell us the moments, what those moments are going to be. And then we essentially have to solve them in a cyclic fashion. X sub 0 is basically known from this. I substitute x sub 1, solve for it, then I basically go n equals 2, by then I'll have solved for n equals 1, so I'll have the lower order moments. So I keep doing this for higher order moments, one at a time, to get the higher order moments. Okay. But this essentially, so basically if I do n equals 0, n equals 0, the spatial moment is equal to 1. If I set n equals 1, notice that if for n equals 1, I have this term, dx1 dt minus 1 or v times dx dt, because it's, this is dx1, this becomes x0, this becomes 0. Okay. For n equals 1, this term is also 0. So for n equals 2, you will have dx2 prime dt, you will have a 2 over here, and you will have this term. And after that, you'll keep involving the lower 2 order moments for your next moment. Okay. Because to compute x sub n, I need to know x sub n minus 1 and x of n minus 2. So I have to solve for these lower moments before I go to the next one, but we can keep doing this. If I do this, in this case, x0 prime is simply equal to 1. x1 prime, remember, the first moment is simply v times t. x2 prime is v squared t squared plus 2 dt, and therefore the variance of the spatial moments based on these is 2 dt. So what we now see is the effective velocity is simply dx1 prime dt. That will give us the velocity. What we think of as dispersion from here, we take the derivative of the variance or derivative of sigma squared with respect to time, that will be 2d. So d is half of this. So this is the result that you basically are familiar with. Either the effective dispersion is going to be half times the derivative of the variance with respect to time. For that to hold true, you have to have an infinite column, and you have to have these conditions. Okay. Otherwise, if you have a semi-infinite column, it will begin to look like this, but after a long time. It doesn't come out immediately because the boundary condition is going to be skewed initially. Okay. Any questions? So when we use these expressions, if we have spatial moments, it means I have essentially data for bulk concentration as a function of time. I divide by small q, make it a travel distance distribution, calculate the moments of those travel distributions, find out what x1 is, x2 is, and so on, and say d effective is going to be this expression, v effective is going to be this expression. I'm calculating this velocity, but these are now Eulerian effective properties. Okay. These are based on spatial moments, not on temporal moments. So we have essentially measured concentrations at different locations, and so therefore this is another way of analyzing it. Any questions? Okay. So what should we do with stochastic convective models? Remember, stochastic convective models did not have the ADE for us. There was no governing differential equation as in the ADE that I could multiply throughout by x to the power of n, integrate each term from minus to plus infinity. I don't have that. For a stochastic convective model, all I did was observe the flux concentration as a function of time at the outer location, and I said I want to do everything just based on that piece of information. So we have to do some more transformations for that, and we can do that because just earlier we found out that the resident concentration and the flux concentrations are essentially related by this expression. Okay. So what I can do is, this is just a transformation of variables. So after I do a little bit of transformation of variables, I find that fr of xt is in terms of f sub f, but wherever I had x, I'm essentially going to write x1, tx1 over x, tx1 over x squared. So I made it a function of x1. But there is some variable transformation that you have to do. But this expression, which allowed us to sort of write the continuity equation in terms of probability densities, travel times versus travel distribution, allows me to do this. So that's why it's so nice. So if I now consider the log normal flux PDF model, log normal flux PDF means we essentially measured our flux concentration at the outer of the column, fitted the log normal distribution to it. It has two parameters, mean and standard or variance, after the data is transformed. If I do this, this is my expression for flux concentration. I can use this to write what the resident concentration distribution should be. And therefore, from this resident concentration distribution, I can calculate my depth moments. In this case, I'm doing depth moments, 0 to infinity. I can compute this, and I'll get an expression. Okay. I can then compute the effective properties using depth moments for stochastic convective models, that would be my Eulerian effective property. Oh, okay. I just want us to remind us, therefore, this is my, so from depth moments, this is what I guess get as my effective velocity. x1 is any distance divided by expectation of 1 over t. Whereas effective velocity in the Lagrangian sense was this one. What happens if y is log normally distributed? So if y is log normally distributed, and you have this as part of your assignment today and perhaps later, this basically all it's doing is giving you some idea of the properties of log normal. So this is its density, we have its expectation, the variance. So basically y is normally distributed random variable, then x is log normally distributed through this transformation, so it has this kind of a probability density. Expectation of x and therefore variance of x, we can easily get them through the moment generating function property of the normal distribution. We have these expressions. So basically notice that x is log normal and y is normal over here. So this allows you to relate, if you are given the expected value of x in terms of, or you can get the expected value of x in terms of the properties of y or vice versa. So the mean and standard deviation of x is given, you can find the mean and standard deviation in terms of y or vice versa. And that is all that is showing, because log normal is one of the PDFs that we look at. The other PDF that we look at is gamma distribution. And again, this is simply giving you the properties of the gamma distribution, which you can use. It has a moment generating function, it has a Laplace transform. Okay. I wanted to also spend a little time on stochastic stream tube models. So for your tutorial today, we are going to be using the advection dispersion equation, the log normal distribution, and the gamma distribution. And we'll talk some more about the properties of tutorial 2. For your tutorial on the 5th day, we'll be talking about stochastic stream tube models. So again, similar idea. So what we are looking at, for instance, is a field where you conduct many experiments, let's say many 1D experiments. And in each of these locations, let's say you are measuring the flux PDF. What is happening is those PDFs are very different, and therefore the values of the parameters of your model, whether it is log normal, whether it's gamma, whether it's the ADE, they are going to be different. Okay? So let's say your local model is concentration, which gives you concentration in terms of x and t, but it has various model parameters. So this could be the velocity, the dispersion, alpha and beta if you are using gamma distribution. It could be mu sub y, sigma y square if it's log normal distribution. Those are all parts of these lambdas. We think of the ensemble concentration over all stream tubes is simply, if all of these are, if I have the joint distribution of all these parameters, this is my definition of the average, ensemble average. Okay. So this is simply the joint distribution. If my local model is not very complicated, it's simply a piston flow model. That means at that location, all solid particles are moving with a velocity v. But this velocity v is changing from one location to the next stream tube, to the next location, to the next location. It has a distribution over the field. Okay? So it's random. So f sub v, let's say, has a PDF. Then c sub f is given by this. And again, by a transformation, I can essentially write it in this form. Okay. So the flux concentration is in terms of the distribution of the velocity. I can find the expected value of the travel times. So that is simply t of x minus v. So I have x over v to the power of n, but since v is a random variable, x is a given distance, I can essentially write it like this. If now v happens to be log normal or gamma or what have you, I can find this expectation. But it is for a very simple piston flow model. Okay. If you have an ADE model, advection dispersion equation model, that means I think at each location, I have advection dispersion occurring, but when I go from one location to the next, I get a different velocity and a different dispersion because of natural variability in the field. What I'm interested in is, well, I have the water table at a certain depth, so over this field, what is the average concentration, flux concentration that is reaching the water table at a certain depth. So I want to be able to do field scale averages. So if I have V and D now, that's two parameters. It's kind of difficult to figure out what their correlation is all the time. So what we do is we do the easier problem first. We first assume that they are completely independent. So if I have 30 measurements of V and corresponding 30 measurements of D, if they are completely independent, then of course this probability distribution will factorize into their individual marginal distributions, and I can do expectations very easily. So that's one limit. The other limit is we assume they're perfectly correlated. Okay. So we'll talk about what we do with perfect correlation perhaps when we come closer to that tutorial. But these are two extremes: completely independent or completely perfectly correlated. Whatever else is happening has to be in between. But these two are easy to do. So we do the easy stuff first. Okay. So I want to sort of wrap it all up with just this quick definition of expected properties. If I have a log normal distribution, that is just as an example, Lagrangian effective properties are in terms of travel times. Okay. So unfortunately I'm using small t. We have been using capital T for travel time. So at a distance x, expectation of t square is essentially the second moment of the travel time. Expectation of t is the first moment of the travel time. Effective velocity is defined as distance divided by the expected travel time. Effective dispersion has this expression. And therefore, if velocity is the only random variable, then we can get fairly straightforward expressions for this. If the resident concentration PDF is obtained, so if I had a log normal distribution, okay, I can basically use this transformation, get the distribution over here, and from that resident distribution I can go ahead and calculate the moments. Effective Eulerian properties are given like this. So VR in this case is the expected value of the velocity. Effective dispersion coefficient is half of the variance of V, how fast that changes with time. Okay. So two ways of getting effective properties. If we are doing column experiments which give us flux concentrations, okay, then we are going to use Lagrangian properties because we are going to do travel time moments. Travel time is a random variable. If I have essentially taken a column, found what the concentration is a function of distance, I'm looking at travel distances, my expressions for effective velocity and effective dispersion are going to be called as Eulerian properties now because they are in terms of travel distances. Okay. That was my last slide. Any questions? You know, this is one thing dangerous about PowerPoint. I could have gone through all of them in 5 minutes and it would be done, but it's very difficult to retain what is going on. Okay. So it's important to take breaks and let it sink in and see if you have any questions. Also want to ask, Professor Guha basically said, from now on, we are going to raise the stakes. The standard is going to get higher. I'm not sure our standards are higher. I'm not sure we are meeting your expectations, but how do you find? Is it too difficult or too easy? Or you don't know? Okay. Any questions? So the level of mathematics is not is not going to be higher than this. So we basically use calculus, integration by parts, change of variables. So basically, straightforward calculus. Our basic concepts are very simple. First is Alice's method. That we can use Laplace transform to calculate moments. Simplifies the problem for us a lot. The second basic concept is when we have travel distances and travel times, how we are able to relate the two, and therefore go from one to the other and calculate spatial moments, knowing information from only one experiment at the outlet. So that's a fairly interesting way of doing this. Any questions? No? All right, well.